Okay, number bases. We need to be familiar with base 10, base 2 and base 16. We need to know how to convert between these and then why we use one of them as a shorthand for the rest. So just a quick bit of background here. The first number system that we can use is called base 2 or binary. It can use two numeric symbols at 0 and 1. The next up, and you don't need to know this, only the ones in yellow here, is ternary. It's base 3. It uses the first 3 symbols. There's quaternary, that uses 4 symbols. Quinary, which is base 5 and uses the first 5 symbols. There's centenary, septenary, octal, nonary, and then we get to the most familiar one, the one that we pretty much all use from a very young age, which is decimal. You'll notice that it's base 10 and it uses the first 10 numeric symbols. Moving on, we have unidecimal, duodecimal, tridecimal, tetradecimal, pentadecimal, and then hexadecimal. From unidecimal onwards, we kind of run out of numeric symbols to use, so we start to use letters in place of numbers. So if we want 11 values, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 values. This A carries on from the 9, so this is 10. In duodecimal, we introduce another letter. So if the A is 10, B is 11, C is 12, 13, 14, 15. So in hexadecimal, base 16, we need 16 numeric values or symbols, which unfortunately we run out of, but we substitute in letters in place of the values, numeric values. So let's start with the one we're most familiar with, which is denary. Denary, the DE of denary, just means 10. So this is base 10. The reason that we use base 10 and learn base 10 from a young age is that we have, most of us have 10 digits. So 10 fingers, 5 on each hand. Now we use, as we mentioned before, the first 10 digits for base 10. Now place values are again what you would have been taught very early on in your life. You start with the units column and then you times that by 10 and you get the next column or place value. If we times that by 10, we get the next place value, and if we times that by 10, we get the next place value. And we can use any of these 10 symbols under these place values. So if I pick this one and put it here, this one and put it there, this one, put it there, and that one, put it there, we've got 3 thousands, 4 100s, 6 tens, and 8 ones, or 3,468. This is a 1, 2, 3, 4 digit number. Okay, so we've used 4 digits to create this number. Next up is binary. So instead of base 10, we moved back down to base 2, which means we can only use the first 2 symbols in that number system. So instead of the place values essentially being multiples of 10, because this is base 2, we multiply them by 2. So 1 times 2 gives us 2, by 2 gives us 4, by 2 gives us 8, and you can carry this on. We can only use 0 and 1. So if I place just at random some 0s and 1s in here, we've got no 8s, we've got a 4, we've got no 2s, and we've got a 1. So if we add these up, that gives us 5. So this is the binary for the decimal value 5. This is, again, 4 digits long, but we don't refer to these numbers as X number of digits long. Instead, we take the its of digits and we just replace it with B from binary. So we essentially end up with bits, or this is a 1, 2, 3, 4 bit number. Okay, if we quickly look into a 1, 2, 3, 4, 5, 6, 7, 8 bit number or binary digits, we can just mark out our place values or our columns and put either a 0 or a 1 put a 0 or a 1 under these. So if you want to have a quick go and trying to figure out what is this binary value in decimal or denary in base 10. So if we add these up, so we've got 128, we've got an 8, a 4, a 2 and a 1. So add 4, add 2, add 1. If we add all these up, that gives us 136, 140, 143. So this binary value, this 8-bit binary value, is much shorter when we convert it into denary. It's only a 3-digit value. So if we want to represent everyday numbers, denary numbers, in a computer, we have to convert them into binary. And this is essentially what the entire unit is about. It's data representation. If we want to represent a denary number in a computer, we have to convert it into binary. Okay, hexadecimal. Hexadecimal is base 16. As we mentioned earlier, we run out when we get to 10 symbols. We run out of digits, so we have to substitute in some letters. So this would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Now, the place values in hexadecimal, again, it's the same principle. You start with your units and you times by the base number. So 1 times 16, times that by 16, times that by 16. And again, you can extend this as far as you like. Now, what we can do here is we can choose from any of these numeric values and pop them into here. So if I put a 3 there and a 9 there, I'll put an A there and I'll put a 1 there. Now this is a 1, 2, 3, 4 digit hexadecimal number. The way that we would add this up is we would do 3 lots of 4096 added to 9 lots of 256, and because this A represents 10, 0, 5, 6, 7, 8, 9, 10, we would do 10 16s, 160, and then 1, 1. Now here are the place values for a 1, 2, 3, 4, 5-digit hexadecimal number. Let's put our place value columns in, and if we pop in here some numeric values, we get 1FC11. To convert this, or to try and understand what this is in denary, we multiply this out and then add them up. So 1 lots of 65,536. Now F, if we think back, F, A was 10, B, C, D, E, F is 15. So this would be 15 lots of 4,096. C, A is 10, B is 11, C is 12. So this would be 12 lots of 256, 116 and 1, 1, and then you add those up. Here is the same number as 1FC11 in binary. The same number again is 130,065 in base 10, and then in hexadecimal I'm rewriting it here, but it's 1FC11. Now if you look at this, these are all the same value. Okay, 130,065. You'll notice in binary it's much longer. We need more binary digits, more bits, to represent this number. In base 10 we need fewer digits to do this. In base 16 we need even fewer digits to do this. And at the beginning we mentioned that we need to know why we would use hexadecimal as a shorthand. Well, because it is shorter, more human friendly and easier to read than longer stretches of binary. So why hex? The main reason we use hexadecimal is that it's more human friendly. Okay, conversion methods. There's lots of different ways to convert between these different bases. So if we start with decimal 10, base 10, and convert it to binary 2 or base 2. So the first method is, if we've got a number, let's say 122, and we want to convert that into binary, we would write out our place values and we just add these up. So we know that 128 is too large, so we start with a 64. And if we add 32, 16, 8 and 1, those total up to 122. Another method we can use is floor division. So floor division, instead of rounding up, if you get a decimal value, you round down towards the floor. So target is still 122. And if we essentially divide 122 by 2, the reason we're dividing by 2 is that we're converting this into binary. So we divide that by 2, and you'll notice that we don't get a decimal here. This is being rounded down. So if we divide by 2, again, we would get 30.5, but we're rounding that down to 30. Divide by 2, divide by 2, divide by 2, divide by 2, and we stop at 1. Now, if we look across these numbers, if we've got a number that is odd, we put a 1 beneath it. So that's an odd number, that's an odd number, that's an odd number. Odd, that's an even number, so we leave that as a 0. That's an odd number, that's an even number. Now we have got 1, 1, 1, 1, 0, 1, 0. This is the binary representation of 122. Phew, got that correct. Okay, moving on. If we want to go from or convert from binary to decimal, there is our binary value, and we want to convert this into decimal. We can simply write in the place values and multiply, then add up the values. So we've got 128, add 64, add 32, add 8, add 2, add 1. I'm only using multiplying out, so 0 times 16, we're not left with a value. So there we've got 235. Okay, so binary to hexadecimal, we start with our binary number. So if we pop that up, there's our binary number. We can use something called the nibble method. We split this 8-bit binary number into 2 4-bits. 4 bits we refer to as a nibble. So there's 2 nibbles, one on the left, one on the right. So if we start on the right hand side, we're just going to treat this as a shorter binary number. So we put our place values in, there's that side, and then we put our place values in for this side. So we're treating them as 2 separate numbers. Now if we look, 8 add 2 add 1 is 11. 11 in hexadecimal, well, we know that 10 is A and B is 11. So we'll pop a B in there. On this side, if we add this up, we've got 8 and 4, which is 12. Add 2, which is 14. 14 in hexadecimal is D. So there we've converted our binary 11101011 into a 2-digit hexadecimal number. The answer is DB. Hex to binary, we essentially do the reverse. So if we start off with F3, we move up from here doing the reverse. What is that in binary? It's 1, 1, 1, 1, 15. And on this side, 3, just 2 and 1. This pops out as F3. Here is a quick knowledge note that's just all the different ways that you can convert between these numbers. Some of them I've not mentioned here, but you should be able to work this out. With the decimal to hexadecimal, you essentially divide the number by 16, floor division, and then just put the remainder in as the next value. We've got the nibble method in both directions here, and we've got a hex straight to decimal there.